Okay, so going back to that table 15.1 and 15.2. And where we left off was this question here on the bottom of the slide. So figuring out some chemical shifts. If we start out with the hydrogen of the hydroxyl group, so an alcohol, if you go back to this table, and that's what we're using, it says that the hydrogen of an alcohol has a chemical shift of around 2 to 5 parts per million. So let's go back here and we'll scribble that in here. It's from 2 to 5 parts per million. Then we have a couple of vinylic protons here. So we have a vinylic proton here and a vinylic proton here. Those vinylic protons are not alpha or beta to any oxygens. And so for vinylic protons, where the heck was I? Vinylic protons have a chemical shift of around 4.5 to 6.5 parts per million. Then we have some allylic protons. So these are all allylic protons. There are 3 protons here. I'm just going to circle all of those and just say allylic. And allylic protons have a chemical shift of around 2 parts per million. Same thing here. These 2 protons are allylic. And so you would say the baseline would be 2 parts per million, but they're beta, right? This is the alpha to the oxygen of the hydroxyl, and this is the beta carbon. And so we add 1/5 of 2.5. 1/5 of 2.5 is 0.5 parts per million. And so we get a chemical shift of around 2.5 parts per million. And then for the last 2, I'll put these ones in green. So the 2 green protons, those have a baseline chemical shift of 1.2 because they're methylene protons. So 1.2 parts per million. And then we add 2.5 because they're alpha to the oxygen of an alcohol. So we add 2.5 parts per million, and we get 3.7 parts per million. Okay, so all of these estimated chemical shifts in here, remember the word that I chose was estimated. And it even says here in the question, identify the expected chemical shift for each type of proton. That doesn't mean it can't vary. Okay, it could be a slight variation on these. It might be a little more deshielded or more shielded, but the idea is that these are very good approximations of chemical shifts. Well, let's move forward and let's talk about what is called integration. So it says integration, if you follow along with me, or the area under the peak quantifies the relative numbers of protons giving rise to a signal. And a computer will calculate the area under each peak, representing that area with what is called a step curve. So you can see that we've got 3 signals here in this NMR spectrum. We have this signal here, we have another one here, one here, one here. And what the computer can actually do, because computers are amazing, the computer can actually calculate the area under this curve. So it actually measures the area under all of these peaks here for this signal. Okay, it'll do it for this one, and then it'll do it for this one. All of what I'm shading in here, it's going to calculate all the area under here, okay, and everything that's in blue, and then it's going to do it for the other 2 signals. I'm not going to shade them in, but then after it measures that area, it gives you a number that is a relative area of all of those different areas. So you see that the relative area here is 27.0, here it's 40.2, here it's 28.4, and here it's 42.2. Now these numbers are not, they don't precisely tell you the number of protons because there's no such thing as 40.2 protons, but what they do tell you is the relative numbers of protons under each one of these curves. Now, if you didn't have these numbers down here, the 27, the 40, the 28, and the 42, in that case, what you would use are these step curves, these lines here, 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 and here. And what a step curve can do is you can actually measure the distance between the top of the step curve and the bottom of the step curve in millimeters. You literally get a ruler out and you measure from the top to the bottom, and you compare the heights in millimeters, and that will give you, again, the relative areas under the peaks. And that relative area, again, is directly related to the number of protons under each peak, or represented, I should say, by each peak. So instead of looking at the numbers 27, 40.2, 28.4, and 42.2, what we do is we take the smallest integration value and we divide every integration value by the smallest. So divide by 27, divide by 27, divide by 27, and divide by 27. And the numbers that we get are 1, 1.48, 1.05, and 1.56. Again, none of these are whole numbers, but they're very close to, the number 1, 1.5, 1, and 1.5. Now again, there's no such thing as half a proton. You can't have 1.5 protons. That doesn't exist. So what would we do with the number? Those numbers, we would multiply all of them by 2, right? Just to get to a whole number. Because if you multiply each one of these numbers by 2, then you get a set of whole numbers. So let's take a look at what that looks like. Go down here and we see we get numbers that are close to 2, 3, 2, and 3. And so what we say now is that the relative number of protons here is 2 to a ratio of 3 to 2 to 3. Now what's interesting here is that even though we have whole numbers, 2, 3, 2, and 3, you might think, well, if I add 2 protons plus 3 protons plus 2 protons plus 3, that gives me a total of 10 protons. So that means I have exactly 10 protons in this molecule. The answer is maybe yes and maybe no. It depends. It might be 10 protons, but it might be some multiple of that. And I'll explain that in more detail in just a second. So let's take a look at a specific case. Let's take a look at this ketone here. You can see that this ketone has an axis of symmetry right here. If you were to rotate this 180 degrees, you can see there's a plane of symmetry in the molecule. And that means that these methylene protons here and these methylene protons here are chemically equivalent. It also means that all 6 of the methyl protons that I'm writing in blue, they are all chemically equivalent. Okay, all of those protons are chemically equivalent. So you might think, well, the ratio of protons that I should see would be a ratio of 4 to 6, right? Because I have 4 red protons and I have 6 blue protons. However, 4 to 6, if we bring it down to the simplest whole number ratio, it would actually be 2 to 3. Now, let's take a look at what the spectrum of this compound looks like. The name of this compound, and we haven't covered ketone nomenclature, that's covered in organic chemistry too. This is called 3-pentanone. Pentanone. All right, so let's take a look at the NMR, the proton NMR of 3-pentanone. Here it is. We have a signal here, and we have a signal here. The signal that's shifted further downfield has 4 little peaks, and the shifted that's further upfield has 3 little peaks. Anyhow, here are their relative integrations, 32.5 and 48. What are we going to do? We're going to divide both of these by 32.5. So if I divide this by 32.5, obviously I get 1. And if I divide this by 32.5, I get 1.48. So you might think, okay, well, I have a ratio of 1 to 1.5. Well, again, we can't have half a proton. So if I multiply both of those numbers by 2, so by 2 and by 2, then I get a ratio of 2 to 3, right? A ratio of 2 to 3. But we know that it's actually not 2 to 3. It's some multiple of that. It's actually 4 to 6. Okay? Again, it just gives you the relative ratios of the numbers of protons. Give me a thumbs up if you follow me on just the concept of integration. The idea that we get the relative numbers of protons. It doesn't spit it out at you. Oh, everybody, here are 2 protons exactly. Here are 4 protons exactly. It could, sometimes it might, but more often than not, we get numbers that we have to work with to determine how many protons are represented. The question that students will ask me oftentimes is, Mr. Dion, may I bring a calculator into the quiz? And I say, absolutely. You can totally bring a calculator in if you need a calculator to help you do a little bit of division. There's no problem with that whatsoever. So let's take a look at a couple of problems here. And these are just questions I ripped straight out of our textbook. This would be the caliber of question that I would expect you to be able to solve. Take a look at 15.11 on the top. It says, A compound with a molecular formula C5H10O2 gives you the following proton NMR spectrum. Determine the number of protons giving rise to each signal. We know in the molecule that we have exactly 10 hydrogens, right? We have 10 protons. Well, if we look at the integration values, they're 33.2, 48.4, 33.3, and 48.7. What are we going to do? We're going to follow the same steps as before. We're going to divide each one of these numbers by 33.2. So divide by 33.2, do it here, and we do the same thing, the same thing here. I'm sure that a lot of you can solve this in your head, but we get 1 here. We get a number that's pretty close to 1.5 here. It's like, what, 1.46 or something. Anyhow, it's close enough. Then we get a number that's close to 1 here, and a number that's close to 1.5 here. Well, if you add up 1 and 1.5 and 1 and 1.5, well, that only gives you 5. And we have 10 protons total. It's not a trick question. Can anybody tell me, what must I do here? How much must I multiply each one of these numbers by? And we have to multiply them all by the same number to get to a total of 10 protons. It is not a trick question. What would I have to do to all these numbers? Exactly. You're all 100% correct. Everybody typed in the chat. They said, Mr. Dion, you need to take everything and just multiply it by 2. Multiply by 2, multiply by 2, multiply by 2. Then you would see that this signal represents 2 protons. This signal represents 3 protons. This one represents 2 protons, and this one represents 3 protons. And just like that, now we were able to take those numbers, all those integration values, and we were able to figure out the exact number of protons that is represented by each one of these signals. The one at 4 parts per million is 2 protons. The one at 2 parts per million represents 3 protons. The one at around 1.6 is 2 protons. And the one that's the furthest upfield at around 0.95 parts per million represents 3 protons. Great, perfect. Let's try the next one. We'll go a little faster because my students really kind of crushed that one. Next one is in a similar vein. Each one of these integration values is shown down here. And we know the formula of the compound is C10H10. So we've got a total of 10 protons. We'll divide each one of these numbers by 17.1, kind of running out of space here, 17.1 and 17.1. I did this one earlier. I had to do a little more massaging of the values here because for this one you get 1. For this one, you get close to 1. Obviously, it's a little more than 1. I'm going to put here kind of close. Close to 1. 87.1. That's not close to 1. Sorry, I can't see. I'm kind of in the dark here. This one's close to 5. This one is close to 1. Not negative 1. What are you doing? Close to 1. And then the last one was close to around 3. And again, I'm kind of in a dark room here. I need to get a desk lamp. But anyhow, so we have 1 plus 5 plus 1 plus 3. Well, that happens to tally up to exactly 10. So that means that this signal here would represent 1 proton. This thing here, that represents 5 protons, probably aromatic. This one here, I kind of overlapped here, but that would represent 1 proton. And then this one here, that represents 3 protons. All right, so there you go, integration. You know, I'll just put this bug in your ear because on your quiz, I'm not going to ask you to get a ruler out and measure a step curve on a screen. That would be insane. But just to throw this bug in your ear, if any of you are taking the lab with Mr. Geiger, and some of you might take the lab with me later on or him later on, something that we do get the students to do once in a while is we actually make them get a ruler out and we say, measure this step curve. We actually have rulers in the wet lab, and we'll make the students get the ruler out and measure it and use millimeters. So if you're the kind of person who likes to peruse the internet and look for more information on everything we do, you might find examples of problems where people do use rulers, but routinely it's something that we do more often in the lab, okay? And even if you take the Organic Chemistry 2 lab, the wet lab at UCCS. In that case, we'd probably give you a question at some point where you'd have to bust a ruler out in the lab and actually measure a step curve. All right. Oh, you want me to tell you something funny before we move on? This is going really way, way back in the day. Not before my time, but, yeah, I guess before my time. Um, I worked with some people who told me that, a long time ago, what they did is instead of having the computer calculate the integration values, they would literally take a pair of scissors. So they take a pair of scissors. Son of a gun. What's going on here? Take a pair of scissors. I was trying to draw a pair of scissors. Okay. And they'd print the NMR out on heavy stock paper. And then they'd take the scissors and they would actually cut out the peaks. So they'd cut this out here along this line, and then they'd cut this one out, and they'd cut all this out on a piece of paper. Okay, Mr. Dion didn't trace it very well. But the idea is that they'd cut all those out, and they would actually mass them on a balance. And they would use the relative masses to figure out the relative number of protons. Again, it's something I've never done, but I know it was done at one point. So that's kind of really old school, but yeah, anyhow, kind of interesting stuff. Something else I'll say, and I mean, I am recording this, so I have no problem saying this out loud to my students, but, out of all the spectroscopic methods that we learned, so we went over IR in chapter 14, infrared spectroscopy. Then we looked at mass spectrometry in chapter 14 as well. And now we're on to chapter 15, which is NMR. And I'd say out of all three of those, the only one that chemists couldn't live without, or I think would be the most difficult, would be NMR. I think it's the most useful routinely, at least for organic chemists, of all the spectroscopic techniques. Let's move on to section 15.7, which deals with multiplicity. And you might have been wondering about these whole, signals, why some of them are 3 little peaks, some of them are 2 peaks, some of them are 4, etc. Well, there's a good reason for that, and that's what we're going to cover now. Therefore, as we move forward, instead of me using the words 2 little peaks and 3 little peaks, I'll use the proper terminology for multiplicity, or the splitting pattern. If we have just 1 peak, I call it a singlet. If we have 2, I call it a doublet. If there's 3, it's a triplet. Then we have a quartet, a quintet, a sextet, and a septet. If you're wondering, is there an octet? We would never see an octet in this class. But these are splitting patterns that we see all the time in Organic Chemistry 1 lecture, in Organic Chemistry 1 lab. You might remember that I showed you one other kind of peak, or signal, I should say, which was the multiplet, which is kind of like, it's where everything was kind of all jumbled together and you couldn't really make sense of it, like this. This is the multiplet. That's something I'll get into later, and I'll explain what the multiplet comes from. It's because of what's called complex splitting, and we're not really